Hello everyone, I'm Xiangli from Tsinghua University. I will talk about SODA, a set of fast oblivious algorithms in distributed secure data analytics. Nowadays, users tend to outsource the computation to the cloud, so users should send their data to the cloud and run the computing framework like Spark, Flink, and so on the cloud for data analytics. However, the cloud could be compromised from both inside or outside, and the attacker can even control the whole system. In that case, both confidentiality and integrity could not be guaranteed. Fortunately, trusted execution environment is a promising way to defend against it. They create isolated environment, and both sensitive data and code reside in it. Even privileged attackers cannot eavesdrop or tamper with the data. Commercial TEs include InterSGX and AMD-ICV. However, TEs are not panaceas. They suffer various side-channel leakage. A major leakage is about access pattern. For example, when the data leaves cache, it will be encrypted transparently by memory equation engine. However, on the memory bus, the attacker can still get the request memory address, and the attacker can also observe the network traffic. Consider in the distributed computing, we group the items in a MapReduce pattern. Given the public information that the number of A are 3 times of the number of B, the attacker can derive the content from the network traffic, and the attacker can finally derive the content of the original partition from the memory access pattern. The common way to solve this kind of side channel is to design specific oblivious algorithms that make the access pattern independent of data content. Many works aim to solve it. However, most of them focus on single machine setting. In this work, we focus on designing oblivious algorithms in distributed setting for data operators, including aggregate, filter, and binary equal join. And in this work, we focus on network traffic instead of memory access pattern because the latter can be solved by existing solutions like CMOV instruction and oblivious sort primitive. So when can we say that we achieve the network traffic protection? Only when we satisfy the following requirement. For distributed filter and aggregate, we require that the traffic be the same, given the same input size and the same output size. That is, the attacker can only use traffic to derive the input size and the output size. For distributed binary join, we have relaxation. We additionally allow to expose the number of the most popular key, denoted by alpha. Here is an example. For the first keyless dataset, alpha equals 2. For the second dataset, alpha equals to 3. Why this leakage is reasonable? Suppose now we perform group by. In the extreme case, all key-value pairs in the dataset belong to one group. If we disallow this leakage, the only solution falls back to the single machine execution to handle the worst case. The execution is no longer in distributed manner. By the way, this relaxation is a common used in previous research work about oblivious distributed join. For distributed oblivious data analytics, we choose opaque as our baseline. There are two partitions, P0 and P1 on different nodes. We aim to fill out items whose key equals to A. Opaque first marks the to-be filtered records by a single scan and perform column sort, and oblivious global sort to put those records to the end, and finally just drop the records. To aggregate items with the same key, opaque also perform column sort to group the items with the same key, and locally aggregate the value. Note that the last item with the same key holds the true value. Since the items with the same key may be distributed across the node, further communication is needed to merge the value. And finally, opaque filters out the dummy value. For the two operators, we notice that the most costly step is column sort, which takes 4 rounds of communication. To remove the costly global sort, we observe that if each node sends the same amount of data to all receiving nodes, we are achieving oblivious net of traffic. Therefore, we propose pseudo-random concatenation, which assigns destination through a pseudo-random function. Different colors in the figure denotes different destination. However, randomness does not guarantee complete uniform traffic, so we apply padding to ensure the same size. Based on the destination of each record, we form the bucket by local oblivious sorts. Buckets in the same partition goes to different destination, and the buckets have the same size. Thus, we met the observation. Since the destinations are randomly assigned, we mathematically derive the necessary padding size to ensure negligible failure rate using Chernoff bounds. In typical case, the padding only adds 10% overhead. However, the key question is, can we randomly assign destination while still achieving desired functionality? For oblivious filter, our key insight is that since filter does not force the destination nodes of each record, we can randomly distribute the records across all nodes. As shown in the figure, grid bounds denotes the records to be filtered, and we directly assign the destination of each item uniformly at random, regardless of whether its records to be filled out. Then, we use Chernoff bound to pad each partition and run pseudo-random communication. After that, we do local oblivious filter to fill out the dummy records in each new partition. Compared to 4 rounds of communication in opaque, we only need 1 round. For aggregate, we cannot directly assign items with random destination. Instead, the destinations are determined by hashing the key. However, the hash-based partitioning exposes record destination and the size of each aggregate group. Our key insight is that in each aggregate group, only one record is needed to hold the aggregate value, while the others can be changed to dummy records. Therefore, as the figure shows, blue band denotes the items with the same key as the next one. After local aggregate, when each last item in the group holds the aggregate value, each last item is assigned using a deterministic hash function, while the dummy records are assigned randomly. And in this way, the overall effect is equivalent to all keys are assigned in a pseudo-random way, like our primitive. So we can invoke pseudo-random communication. Finally, we only need some local oblivious processing. During the whole procedure, we only need 1 round of communication instead of 4 rounds. Now we turn our focus to join. Opaque only supports primary foreign join. It first globally sorts all key-value pairs based on the keys. For the same key, records in table A are in front of records in table B. Then a single scan is performed to prepare for join. Here, the cross-node communication is also needed, for the case where the records with same key spanning multiple nodes. Since it's a primary foreign join, the join product size is fixed. However, when extending it to binary cojoin, changes emerge. The communication traffic depends on the key distribution. Here, we have 3 pairs in the table A with the same key. All of them need to be transferred, and the join product size depends on the join degree for each group. So here are 2 kinds of skewness. One for the number of input records, and the other for the number of output records. To solve the two-skew needs, we propose two-level assignment. Given two tables A and B, we count the size of each group, and bin pack the groups into bins with capacity determined by the most popular key. And we fill the rest of the bins with dummy blocks. Therefore, after the first level assignment, each bin has the same number of records. Then, we calculate the join product size of each bin, and dispatch two bins to one partition and other two bins to the other partition, while balancing the join product size. Note that the join result will also be paired to the same amount. Therefore, after the second level assignment, each partition has the same number of bins, and each partition has the same total join product size, solving the two-skew needs. Moreover, the assignment process runs before the data shuffle occurs, and works on metadata rather than data. The process itself is implemented to be oblivious. The overall workflow is shown in the figure. First, we randomly shuffle the items to reduce the bundle padding. To count the group size and join product size, we perform oblivious aggregate to get metadata statistics. Then, we perform two-level assignment based on the statistics and record the destination node for each item in field B in the figure. And the assignment results are patched back to the original items. Next, the original items shuffle based on the assignment. And finally, we do local oblivious join. For more details, please see our paper. For evaluation, we test our system on both individual operators and macro benchmarks. For aggregate and filter, we achieve about 2 times speedup, mainly due to the communication reduction. For binary equal join, we achieve speedup range from 1.5 times to 3.7 times. It mainly results from padding reduction. For macro benchmarks, which may comprise multiple kinds of operators, speedup range from 1.1 times to 14 times. Join dominates the cost. To summarize, we propose a co-preemptive called pseudo-random concatenation, which randomly assigns destination to each item and pad each partition to Chernoff bound. And we propose oblivious filter, which randomly distributes the records. And we also propose oblivious aggregate, which turns the all but one records in each group into dummy records. And finally, we design oblivious binary equal join by proposing two-level assignment to solve the two-skew needs. Thank you.